Okay, let's prove this division algorithm. Okay, so the example here is 33 is equal to 7 times 4 plus 5. So my remainder is 5, which is greater than 0 and less than 7. My quotient is 4, and we're going to say that I would need to tell you in this case that that's obviously unique. But let's pretend we don't know much about these numbers. We're just going to analyze how the possible structure of this number could be, and we're going to show by contradiction that so that means I'm going to make a claim that proves to lead to something stupid or something that's obviously false and breaks down all the other rules, so the opposite must be true. Okay, so we're going to prove by contradiction that that Q and R are unique, where B is equal to A times Q plus R, and R is between 0 and so it's between 0 and A. Okay, so if they weren't unique, let's make a claim. Okay, so let's say that there exists a different set of like another quotient, we'll call it Q1, and it has this other remainder. Okay, and so once again this remainder is also between 0 and A. Okay, otherwise we don't have a remainder, or we change our quotient or whatever. Okay, so that's why we know that our final remainder will be in that range. Okay, so if that was true, then because they're both equal to B, that means that A Q1 plus R1 is actually equal to A times Q plus R. So if I subtract the AQs from both sides and the R1s from both sides, then that's right. Yes, then we just all we need to do is now factor out the A, and now let's imagine that let's assume, because if these aren't the same, okay, these are unique, so let's assume that R is greater than R1. Okay, so that means that this number here, because these are also unique, right? So Q1 and Q are unique. So there's some number here, some integer number times this integer A. So that means that, we'll call this equation 1 so you know what I'm talking about. So by equation 1, well, I'll just write 1. So by 1, R minus R1 is a factor. Sorry, is a multiple. Sorry, is a multiple of A. Now, that doesn't make sense because R is greater than, R is greater than A. Sorry, R is between 0 and A, and so is R1. Okay, so if R is greater than R1, and if they're not equal, then it has to be a number between R and 0. Okay, the right hand side of this equation. So how does that work if it's going to be between 0 and R, and R is less than A, that this number is between 0 and A, and be a multiple of A. That just doesn't make sense, all right? So it's a contradiction, okay? And just like in the same way, I could have I could also rewrite that initial equation up there to say that I could have the AQ and subtract the A1s over. I could rewrite this to say that R1, and I subtract the R to this side, and I could subtract the Q1 over to the other side, AQ, sorry, minus AQ1. And then factor out if I could say then if assuming that R1 is greater than R, I'm going to also get to the point where we'll call this equation 2. I could also say that R1 minus R is a multiple of A, which doesn't make sense if these numbers are between 0 and A, okay? Because it's going to be a number between 0 and R, which is less than A, okay? So that doesn't make sense. So in both these cases, let me pause while I write this, so I won't make you sit through this. Which means that, so in other words, we're saying that if R was greater than R1, that it can't be between 0 and A, and then it's R minus R1, it's between 0 and R, obviously, and a factor of A. That just doesn't make sense. That and are a factor of A, okay? So by contradiction, we have shown Q and R are unique. Voila! Welcome to your first contradiction, proof by contradiction. Ciao, ciao.